So we now move to the regular programme, and we start with the RAS Norman Lockyer Research Fellowship 2014 lecture, and it will be given by Dr. Rowan Smith of the University of Manchester. The title is Filaments and Dark Gas, the Environment of Star Formation in Spiral Galaxies. Welcome.
There we go. The wonders of technology. So first of all, I'd like to thank you very much for having me here, and also through the fellowship, the RAS Norman Lockyer Fellowship, for making a lot of this work possible. So it's really lovely to show it off to you today. So as my title says, I'm going to be talking to you about filaments and dark gas, and really the environment of star formation in spiral galaxies. So to start off, it's always good to start with a bit of motivation. You know, why are we doing this? It's always a good question to begin with. I always like to just remind people why star formation is a really fundamental process. Now, of course, it's interesting and fascinating in its own right, but it also has a real interplay with lots of different areas of astrophysics. So stars, of course, produce all the heavy metals in our universe in their core. So if you want to understand how metals became in the universe, how rocky planets like our own is formed, you maybe want to know about metal enrichment. You might want to look at planet formation because, of course, planet formation is a little byproduct of star formation. You might be more of a cosmologist. You might be interested in how galaxies evolve. And the feedback from these stars is going to be really fundamental to help set your internal dynamics. Or maybe you're interested in the reionization of the universe, which of course takes place through stars. So this is a really fundamental process that kind of threads its way through all astronomy. However, of course, there is one big challenge. Because of that very interplay, it is quite hard to study in isolation. So I've put up here the Rhine, nearby star-forming region, one of the closest regions that can form massive stars. It's very pretty. And this size scale here is about 0.003 kiloparsecs. Now, this is part of our Milky Way galaxy, which is a spiral galaxy. This is M51 here, another observation of a kind of spiral galaxy. And this is 18 kiloparsecs. So those are obviously very different scales. But if we look at where molecular clouds form, these regions where the stars form, if we look along the spiral arms and the dust lanes, we see these red sites, and those are all sites of star formation. And so this structure is having an impact on where these star-forming clouds can form. However, it's not a one-way process. This region here has formed massive stars. When that forms, it's going to explode, injecting lots of energy into the galaxy, which will then influence its dynamics. And so you have this cyclical process. And the galactic structure also has an effect on the morphology of the clouds. Often when we think of a cloud, you can think of something that's nice and puffy. You know, I'm a theorist, so I naturally think it's a sphere in a vacuum. But actually, when you look at these things, you see that they're actually long and filamentary. The top image here, this is the Nessie Nebula, which as a Scot, I am contractually obliged to bring up at every single talk. As you can see, it's beautifully, just like Nessie. Here's the head, yeah? And this is a nearby star-forming cloud. Well, and you can see it has this long filamentary morphology. Here are some more examples of clouds, and here are some little tiddly ones. And they're just all over the place. Whenever you look at clouds, you very often see that they're long and strung out. And there seems to be a correlation with galactic structure. So if we're to plot the location of some of these filamentary clouds this is done by Wang et al. In 2015, you can see that they do tend to lie over where the spiral arms are predicted to be. And more than that, their orientation looks like they probably lie along them. So once again, we see this interplay between the sites where stars form and the larger galaxy where they're hosted. There is a further complication, however, which I want to just go into before we go into my own work, and that's molecular clouds, of course, are made of molecular hydrogen, H2. The problem is, at the temperature of these cold clouds where the stars form, there isn't enough energy to excite emission lines. And so you have to look for a secondary proxy, which in this case is normally CO. The trouble is that CO does not have the exact same properties in terms of its chemical shielding as molecular hydrogen. It requires a certainly slightly higher column density in order to shield itself from the interstellar radiation field and stop it from being dissociating. And this means that if you have a nice theoretical cloud here, this lovely sphere, and your radiation field is coming in from the outside, you'll get this shell round about the star-forming cloud in blue, where we have molecular hydrogen, which is what we think of as where stars form, but there's no CO. And so if you observe this region, this shell in your telescope, it's what we call CO dark. It's molecular gas that you can't see, so it's just missing from your observations. So that's a further complication to observing these things. It's not just finding with your telescope, you have to account for the fact there's matter you cannot see. So to study this, I use a numerical approach. So I do simulations of how molecular clouds form and fragment to form stars, and as part of the fellowship, I've been looking at this in a galactic context. And I've called this here a cloud factory, because the simulations I give are not going to be perfect simulations of galaxies. The point is to look at an environment similar to a galaxy, which will have the same conditions acting upon the cloud. And to do this, I use this simulation software called a repo. It's a magneto hydrodynamic code. For the moment here, I'm just using the hydro part. And in this, we solve the fluid equations to look at how the gas flows and moves using a mesh which moves. So as a wee 2D example here, here's a video of the Kelvin-Helmholtz instability. And if you can see that individual cells move along with the gas. And the reason why that's important is because of this flow, we can have our resolution exactly where we need it. And we can add additional refinement, all in one grid, while still resolving fluid instabilities accurately. And this is one of the reasons which allows us to resolve that problem I told you at first, that there are many different scales in this star formation process. So that's which allows us to look at both molecular clouds and larger galaxy scales in the same simulation. So these are the simulations. As you can see, that's not a proper galaxy yet. What I've basically done is cut a hole in the middle and just looked at the dynamics in a kind of torus. And in this region, there's one region here which is at high resolution, and that just rotates along as the galaxy rotates. And this is where we do all our analysis, in that highly resolved section. So to the base hydrodynamics, we've added several different flavours. We have time-dependent chemistry, UV, cosmic field, external spiral potential, which gives us this, and refinement. These simulations don't have gas self-gravity, they've just got the global gravity, and they don't have supernovae here, but I'll show you some supernovae later. Okay, so to go straight to the results, because we include chemical network in this simulation, we can actually look at the different components of the interstellar medium. So this shows you H1 in this highly resolved section of the galaxy disk. You can see the spiral arms here, and the gas will flow through like this. Okay, and this here shows you the molecular hydrogen. And that's the environment in which we think stars form. So straight away we can see that H2 is much more tightly confined to the arms than the H1 emission. Then we can go on to look at the molecular hydrogen, these molecular clouds where the stars form in more detail. And again, we see this filamentary geometry, which we saw in the observations. So that's just a blow up of several different regions of the simulation. And you can see these long filamentary clouds. You can see a very dense region where the spiral arm is, and then material gets sheared out of the arms, forming these spurs. As I said, that's the molecular hydrogen. That's where the molecular clouds are. But what would you actually see if you were to observe a spiral like this in your telescope in terms of the CO? Where would you see the CO emission? This shows you it here. So all the stuff in grey is where you have hydrogen, molecular hydrogen gas. All the stuff in kind of purpley pink, which is very on brand for Manchester, shows you where the CO emission is. So every place you can see grey, but there's no purple on top of it, that's CO dark gas. That's material which is just completely missing if you observe this. It's this kind of missing component. And using these simulations, we can try and make an estimate of how much mass we might be missing. And this would give us our CO dark gas fraction. So if we integrate the H2 mass up into the point in which the CO suddenly turns on and becomes bright, we can see that 42% of the molecular hydrogen has a CO emission of less than 0.1, so you wouldn't see it in your telescope. So 42% of the molecular mass in a spiral galaxy, such as the Milky Way, you won't see in your telescope. That's the CO dark gas. I quite like the fact it was 42%, because it allowed me to cite Douglas Adams. So he should be on the archive now, because I got that past the editor. The only thing he wanted was to check the address of the publisher, which shows you priorities. The other interesting thing is to kind of, okay, I've got a number, wonderful, 42. Answer to everything. It doesn't tell you very much. The other thing that's interesting is look at the physics of why we have this material. And we can see that this filamentary geometry is having a real effect. Because if you think, what's happening is the interstellar radiation field has to penetrate the cloud to dissociate the hydrogen. So if you have a sphere, that centre is shielded on all sides. Now, if you have a filament, of course, it only has to penetrate through the short axis. And so you can see that actually this filamentary geometry encourages the CO to be dissociated, and that helps keep the dark gas fraction high. And the other thing which is interesting is it means that when we see these observations, the long filamentary clouds are really just like the tips of icebergs floating in the sea. There's an awful lot more underneath. And if you look at the thermodynamics of this material, that's really interesting too. Because it's at a temperature, so your CO is at a temperature about 16 kelvins, and your H2 in the dark gas region is about 60 to 100 kelvins. And so you have this cocoon of warm material around the cloud. And what means that is if you then shock this, if you bring it together and increase the density, it's a lot easier to compress this than if it were hot atomic material about 10 to the 4 Kelvin. And so because you have this cocoon surrounding cloud, it's a lot easier to make more clouds. You just need to nudge them together a little. So I think that's a really interesting feature of this. And of course, if you look at other cases, so like other galaxy types, we find actually this could be even more extreme. So if we look to the case of if it's got a strong field and a low density case, in those cases we found that there was even more CO dark gas, maybe up to 80%, and that there was an even bigger difference in the temperature of the two phases. So the final thing I want to say on this work on a large scale is that it also allows us to relate cloud positions to this galactic structure. To go back to the Nessie cloud, which I showed you at first, this here, if you can, it's not come out very well. This here is the Nessie, and the white line shows you where a spiral arm of the galaxy is. And there is a supposition that when we are actually observing this 100 parsec long molecular cloud, we're actually seeing the spine of one of the spiral arms of our Milky Way. And so maybe if we can detect other clouds like this, we can use them kind of as anchor points for our understanding of spiral galaxy structure within the Milky Way, which of course is really hard because we're embedded in it, we're not looking at it from outside. So we've looked at that using my simulations as well. That's an example of a region which is in a similar position to Nessie. We've taken such a region, looked at its properties, rotated it by different viewing angles, and yeah, it does seem to be quite similar. So at the moment we're trying to characterise how common that might be, and we find that the typical lengths, column densities do look similar between the two cases. So we're exploring this a bit more to try and understand if we can link the molecular clouds to this galactic structure some more. So that's why galaxy context is so important. I'm now going to take a bit of a step backwards to look at how we've been studying how stars form in individual molecular clouds. I'm going to go back to the galaxy scale at the end. So to do this, we have studied star formation in molecular clouds using a highly technical process of taking a box of gas and then shaking it. Yes, basically what we do is we take a given density, put in all the right physics, and in order to understand the turbulence, you apply a power spectrum with the hand of God, which matches the observed relations seen in nearby molecular clouds. So for such a cloud, this is my simulation of how that cloud in isolation collapses and fragments. And again, you can see it's back to this theme of filamentary structure. You see this running through the cloud. And again, in the observations, you see the same. This is some observations using the Herschel Space Telescope by Doris Arzamanian. And you see these networks of filaments throughout the cloud, which when you look at in detail, you can see individual stars forming at, just like beads upon a string. And so once again, there's this interplay between the structure of your molecular cloud and the stars that form within it. And you can see this very clearly within the clouds. So these are my simulations, and these kind of spaghettiograms on the right show where I've identified filaments in the different colours. And if we relate where these structures form to the stars, I've shown here, if you can maybe see all the crosses, again you can see they're forming like beads upon a string. If you look at the arrows, this shows you that in order for these protostars within the cloud to form, this structure is really important. Because what it's doing is it's kind of channeling mass towards the stars. So if you want to look at where the most massive stars, those ones which give feedback to the galaxy, are formed, what we find is that they're formed at the end, at the junctions of filaments. We find that there's streams of gas flowing through these filaments towards the massive protostar star. This allows them to have a high accretion rate, and because the mass is coming in from certain regions, it's not so affected by radiation pressure, and it allows them to grow beyond the initial core mass. And so what we want to do to feed back to that galaxy understanding is to kind of combine the two and no longer do magic simulations where we put the turbulence by hand, but to look to see if we see this sort of structure within the galaxy simulations and really relate that to how it's going on. So that's what I did as part of my RAS. This is what I'm doing now. We're trying to unite these two. This is some new simulations. This is work in progress, so it's still very dirty. This shows you spiral galaxy. Where all the blue dots are, that's where sites of star formation are. And here we have the same thing, but we now have the supernova feedback, we have the gas collapsing. And what I can do is I inject kind of flags of tracer particles within this. And we have a very high resolution within that, which at the moment is down to 1 parsec, but I'm aiming to go better. And we can follow these regions as it goes through the gas. And so here we have molecular clouds which are extracted from a truly galactic environment. So looking at face down, we can identify where filaments form within them. This is viewed as would be within the disk. You can see very reminiscent of one of the kind of filamentary clouds that I was showing you. And we can start to analyse the properties of these and try and look at how this will affect the star formation within it. And even better, we can aim to look at other environments beyond just our Milky Way disk. This is some work by Matthias Samani, who I work with, looking at the galactic centre, predicting what the molecular gas will be like in this regime over time. And we're looking at where star formation will occur in this environment. And of course, we can also look at other galactic systems. And this is simulation by Robert Tretz, who I work with now, looking at a formation of a kind of flocculent galaxy. And again, this has got our time-dependent chemical model in it, so we can relate the galaxy structure to where the actual molecules and molecular clouds form. So just to summarise, first of all, thank you very much for allowing me to do that for my fellowship. I hope today I've shown you the morphology of molecular clouds are intrinsically related to galactic structure. Almost half of the H2 in spiral galaxy disk like our own is CO dark and so invisible to observers. Filaments with molecular clouds feed gas towards stars for accretion. And to truly understand star formation and galaxy evolution, we need to study the two together. Thank you very much.
Thank you very much indeed. We have a few minutes for questions or comments. Microphone.
Would this scale up to even larger scales in galaxy formation, and you tend to get sort of filaments in galaxy clusters, filaments of galaxies?
Yes, actually a lot of the filament identification tools which I'm using were developed from that cosmological context. It is slightly different because in the galaxy case, you're dominated really purely by gravity. So those are filaments due to your gravitational collapse. In these cases, we find that a lot of the structures come from other forces. So in the galaxy, we're often looking at shear. We have a blob, and then as it rotates, the differential rotation stretches it out. Within the clouds, what you're really looking at is the internal turbulence. One of the things which I find is really exciting, which I didn't have time to go into, is I think you can maybe relate the formation of these filaments to the actual velocity fronts moving through the cloud. So it might even tell you something about the turbulent cascade. So in the cosmological case, it's nice and clean because you've only got one force. Whereas
Yes.
Within the ISM, there are many different forces which unfortunately will all give you filaments.
Could I just ask you, the observational data, I didn't catch all of the facilities that you use. You mentioned...
I don't take it. I'm a pure theorist. I leave this to the experts. You don't let me near data. Make my own. You mentioned Herschel, for example. Herschel was really revolutionary in that for the first time you could really see the dust emission properly, and you weren't always doing this background subtraction, which tend to just highlight the cores. When people suddenly looked at these clouds in Herschel, it was a bit of a game changer because suddenly you could see all these threads and filaments which previously had just been subtracted out. So it was really, really exciting. And then for the galaxy surveys, you're looking at any large MCO survey. Something that's really exciting is ALMA, because now means that in nearby galaxies, you can actually go down to almost parsec, 10 parsecs, so even better resolution, which means that we can start to try and do some of the work we've done on the Milky Way in external galaxies. And of course, that should really help us understand star formation.
Okay, well, thank you very much indeed.